Hello and most welcome to Heidegger 1230, and we are recording in this lovely setting in Trädgårdsföreningen, just around the corner of the main building. It's a grayish typical November sky, bit windy, but above all incredibly warm. This is strangely for the season. We're speaking 1st of November today, and I'd say it's at least 14-15 degrees. Not actually a need for winter clothing at all. I would today bring up the opponent of Julian Barber. His name is Lee Smolin, and I guess you're probably already familiar with him in some way or another. In contrast to Julian Barber, Lee Smolin says that time does actually exist. But although this sounds like clashing views, you'll see during the lecture here that the differences are not as sharp as you might think. There are indeed parallel things here that are going on, and it depends on what you mean by time, or it depends also what you mean by space. This first one is not really about time. It's something called the cosmological problem, and you will soon hear what that is about. It's an article by Amanda Gefter from the Quantum magazine, 27th of June 2019. And you will hear already in the beginning where we are heading. How to understand the universe when you're stuck inside of it. It's put on Instagram by Amanda. I will repeat it. How to understand the universe when you're stuck inside of it. Lee Smolin has a radical idea for how to understand an object with no exterior. Imagine it built bit by bit from relationships between events. The universe is a kind of an impossible object. It has an inside, but it has no outside. It's a one-sided coin. This Möbius architecture presents a unique challenge for cosmologists who find themselves in the awkward position of being stuck inside the very system they're trying to comprehend. It's a situation that Lee Smolin has been thinking about for most of his career. As a physicist at the Perimeter Institute for Theoretical Physics in Waterloo, Canada, Smolin works at the knotty intersection of quantum mechanics, relativity, and cosmology. Don't let his soft voice and quiet demeanor fool you. He is known as a rebellious thinker, and he has always carved his own path. In the 1960s, Smolin dropped out of high school, played in a rock band called Idio Plastos, published an underground newspaper, wanting to build a geodesic dome like R. Buckminster Fuller. Smolin taught himself advanced mathematics, the same kind of math it turned out that you need to play with Einstein's equation of general relativity. The moment he realized this was the moment he became a physicist. He studied at Harvard University and took a position at the Institute for Advanced Study in Princeton, New Jersey, eventually becoming a founding faculty member at the Perimeter Institute. Perimeter, in fact, is the perfect word to describe Smolin's place near the boundary of mainstream physics, when most physicists dived headfirst into string theory. Smolin played a key role in working out the competing theory of loop quantum gravity. When most physicists said that the laws of physics are immutable, he said they evolve according to a kind of cosmic Darwinism. When most physicists said that time is an illusion, Smolin insisted that it is real. Smolin often finds himself inspired by conversations with biologists, economists, sculptors, playwrights, musicians, and political theorists. But he finds his biggest inspiration perhaps in philosophy, particularly in the work of the German philosopher Gottfried Leibniz, active in the 17th and 18th centuries. Who along with Isaac Newton invented calculus. Leibniz argued that there is no fixed backdrop to the universe, no stuff of space, Space is just a handy way of describing relationships. This relational framework captured Smolin's imagination. As did Leibniz's enigmatic text, the monadology. In which Leibniz suggests that the world's fundamental ingredient is the monad, a kind of atom of reality, with each monad representing a unique view of the whole universe. It's a concept that informs Smolin's latest works as he attempts to build reality out of viewpoints, each one a particular perspective on a dynamically evolving universe. A universe as seen from the inside. Smolin works out a simple calculation in his causal theory of views. Very important. Causal theory of views. The theory describes the information each event has about events in its immediate past. Which is called the view of the event. The universe grows by the continual creation of new events following a law that maximizes the diversity of all these partial views of it. Your work, she asked, has been very influenced by philosophy. Looking back historically, people like Einstein, Bohr, John Wheeler, all took philosophy very seriously. It directly influenced their physics. It seems to be a trait of great physicists, and also of not great physicists. Okay, fair. It just seems that it's become almost a taboo to talk about philosophy and physics today. Has that been your experience? Not at all. Many of the leading theorists in foundational physics, where the goal is to deepen our knowledge of the fundamental laws, know philosophy very well as an undergraduate at Hampshire College. I did a lot of physics and some philosophy courses. We had a little gust of wind there. I'm very sorry about that. I will continue with the interview of Lee Smolin. Then I went to Harvard for graduate school. I intended to do a double PhD in physics and philosophy. It reminds me a lot of work that's going on now in physics that's finding surprising connections between entanglement and the geometry of space-time. I think a lot of that work is really interesting. The hypothesis that's motivating it is that entanglement is fundamental in quantum mechanics, and geometry of space or space-time emerges from structures of entanglement. It's a very positive development. You said that these ideas were inspired by Leibniz's monodology. Did you just happen to pull out your monodology and reread it? I first read Leibniz at the instigation of Julian Barber when I was just out of graduate school. First I read the correspondence between Leibniz and Samuel Clarke, who was a follower of Newton, in which Leibniz criticized Newton's notion of absolute space and absolute time, and argued that observables in physics should be relational. They should describe the relations of one system with another, resulting from their interaction. Later I read monodology. I read it as a sketch for how to make background independent theory of physics. I do look at my copy from time to time. There is a beautiful quote in there where Leibniz says, just as the same city viewed from different directions appears entirely different, there are, as it were, just as many universes. Which are nevertheless only perspectives on a single one, corresponding to the different points of view of each monad. That, to me, evokes why these ideas are very suitable, not just in physics, but for a whole range of things, from social policy and postmodernism, to art, to what it feels like to be an individual in a diverse society. But that's another discussion. You have a slogan. The first principle of cosmology must be, there is nothing outside the universe. In different formulations of the laws of physics, like Newtonian mechanics or quantum mechanics, there is a background structure. Nota bene here. This is not an easy thing. Structure which has to be specified and is fixed. It's not subject to evolution. It is not influenced by anything that happens. It's structured outside the system being modeled. It's the framework on which we hang observables. The observer, a clock, and so forth. The statement that there is nothing outside the universe, there's no observer outside the universe, implies that we need a formulation of physics without a background structure. All the theories we have, in one way or another, apply only to subsystems of the universe. They don't apply to the universe as a whole, because they require this background structure. If we want to make a cosmological theory, to understand nature on the cosmological scale, we have to avoid what the philosopher Roberto Unger called the cosmological fallacy. The mistaken belief that we can take theories that apply to subsystems and scale them up to the universe as a whole. We need a formulation of dynamics that doesn't refer to an observer or measuring instruments or anything outside the system. That means we need a different kind of theory. You recently proposed such a theory, one in which, as you put it, the history of the universe is constituted of different views of itself. What does that mean? It's a theory about processes, about the sequences and causal relations among things that happen. Not the inherent properties of things that are. The fundamental ingredient is what we call an event. Events are things that happen at a single place and time. At each event, there's some momentum, energy, charge, or other various physical quantity that's measurable. The event has relations with the rest of the universe. And that set of relations constitutes its view of the universe. Rather than describing an isolated system, an isolated system in terms of things that are measured from the outside. We're taking the universe as constituted of relations among events. The idea is to try to reformulate physics in terms of these views from the inside. What it looks like from the inside of the universe. How do you do that? There are many views, and each one has only partial information about the rest of the universe. we propose as a principle of dynamics that each view should be unique. That idea comes from Leibniz's principle of the identity of indiscernibles. Two events whose views are exactly mappable onto each other are the same event by definition. So each view is unique, and you can measure how distinct one is from another by defining a quantity called the variety. If you think of a node on a graph, you can go one step out, 2 steps out, 3 steps out. Each step gives you a neighborhood. The 1-step neighborhood, the 2-step neighborhood, and the 3-step neighborhood. So for any 2 events, you can ask, how many steps do you have to go until their views diverge? In what neighborhood are they different? The fewer steps you have to go, the more distinguishable the views are from one another. The idea in this theory is that the laws of physics, the dynamics of system, work to maximize variety. That principle, that nature wants to maximize variety, actually leads within the framework I've been describing to the Schrödinger equation. Hence to a recovery in an appropriate limit of quantum mechanics. I know from your book, from the journalist, that you are a realist at heart. You believe strongly in a reality independent of our knowledge of it. And therefore, like Einstein, you think quantum mechanics is incomplete. Does this theory of use help complete what you think is missing in quantum theory? Einstein, as well as someone called Leslie Ballantyne, advocated an ensemble interpretation of the wave function. The mathematical object that represents a quantum system. The idea was that the wave function describes an ensemble of possible states. But one day I was sitting in a cafe working, and I thought, what if the ensemble is real? What if, when you have a wave function describing a single water molecule, it's actually describing the ensemble of every water molecule in the universe? So whereas normally we would think that there is one water molecule but an uncertainty of states, you're saying that the uncertainty of states is actually the ensemble of all water molecules in the universe. Yes, they form an ensemble because they have very similar views. They all interact with one another. Because the probability of interaction is determined by the similarity of views. Not necessarily their proximity in space. Things don't have to be near each other to interact. In this theory, the similarity of views is more fundamental than space. Often two events have similar views because they're close in space. If two people stand next to each other, very important, they have very similar overlapping views of the universe. But two atoms have many fewer relational properties than big complex objects like people. So two atoms far apart in space can still have very similar views. That means at the smallest scale there should be highly non-local interactions. Which is exactly what you get with entanglement in quantum mechanics. That's where quantum mechanics comes from, according to the real ensemble formulation. passage from the monodology that has inspired Smolin's latest work. Bit of short pause here. Say the most important take here is the cosmological fallacy, also something put forward by Unger, and it's devastating, I would say. It's maybe the greatest contrast to what I usually call multiverses or mathematical universes. Do you take mathematical in the sense of that the laws are mathematical, not that there is anything wrong with using mathematics in physics. Those are two entirely different things, not to be confounded. There is another article here that might help with the understanding of the cosmological fallacy. It is from a page called Adam's Optics. I think it's funny formulated. On time reborn as a modern myth, Wiley Smolin may be right about physics, but probably wrong about free will, consciousness, computers, and the limits of knowledge. The renowned mythologist Joseph Campbell once argued that any existential narrative worth its salt must combine four essential elements: the cosmological, the psychological, the sociological, and the mystical. A good myth must also soothe the psychological pains of existence, answer the sociological questions of how to live as part of a group, and crucially suffuse our lives with a mystical awe, such that through every feature of the experienced world, the sense of an ideal harmony resting on a dark dimension of wonder should be communicated. In the 21st century, our cosmologists are rather more humble. Though their theories may strive to provide our most accurate and comprehensive view of nature and the sort of mystical wonder that Brian Cox, another physicist, does well to bang about. The majority of scientists shun the notion that their every discovery ought to comfort us or tell us how to live. This is a very good thing in my view. Maintaining a distinction between what there is and what we ought to value protects both our science from wishful thinking and our ethics from God on our side, dogmatism, or nature on your side, or what have you. So when a theoretical physicist publishes a book that promises not only a potential solution to the language-standing puzzles in physics and cosmology, but also a scientific reinvigoration of free will and human agency, and on top of that, a series of deep insights into the problems of politics, social organization, economics, climate change, and our personal lives. Well, I think it's sensible to be cautious. Lee Smolin's Time Reborn is science as modern myth, and draws its philosophical vigor from a revolutionary physics of time that overturns universal determinism and asserts the absolute reality of the present moment. Or something. Smolin freely admits that he is not a philosopher, but that his work aspires to be philosophical. But philosophy is a dangerous business for eminent scientists. A point well made by Daniel Dennett. Quote here, "The history of philosophy is the history of very tempting mistakes made by very smart people. And if you don't learn that history, you'll make those mistakes again and again and again." One of the ignoble joys of my life is watching very smart scientists just reinvent all the second-rate philosophical ideas, because they are very tempting until you pause, take a deep breath, and take them apart. Many of Smolin's philosophical ideas, I would like to suggest, are nothing new. And have either been put forth or persuasively debunked by numerous philosophers, including Dennett himself. That said, his science is fascinating, and what I like to do now is to try to sift the best of Smolin's scientific ideas out from what I am convinced is some sadly shaky philosophy. But before I do that, I should mention that I had the great pleasure of attending a talk by Smolin as a part of the Bristol Festival of Ideas. And not to mention a wonderful orator. So let's go into the zest of it. Timeless mathematics and the computer universe. So what is Smolin's big idea? In his own words, that time is real. Well, of course time is real. You may be tempted to respond. And whoever said that it was illusory. Well, according to Smolin, that's exactly what physics has been saying ever since Newton. The Newtonian paradigm is one that suggests that the future may be calculated with perfect fidelity from two inputs: accurate knowledge of a system's initial state, plus the application of physical law. This is what Newton himself achieved. With the planets and his laws of gravity and motion. Take the position of the planets around the sun at any one moment. Apply the laws, and it's possible to predict their future positions indefinitely. The same logic underlies general relativity, the standard model of elementary particles, and quantum physics. Although the latter is contentious. So what does this say about time? Well, here's the bombshell. Any version of physics that claims to be able to predict the universe with timeless logic has done away with time completely. If the history of the universe is a perfect continuum, equivalent to a perfectly logical deduction, then there is no such thing as the present moment. And the universe may as well be a computer, or perhaps a mathematical structure. Computer is the proposal of David Deutsch, or mathematical structure is Max Tegmark. So what's wrong with that? The usual and, as I will argue, fallacious objection runs that an entirely deterministic universe denies free will. And indeed Smolin goes along with this. In fact, at one point in his Bristol talk, Smolin conceded that the secret history of this project was to offer some cosmological support to the work of Jaron Lanier. A computer scientist whose one half a manifesto 2000 pits itself against evolutionary psychology and its attendant vision of human beings as biological computers. I actually think that the analogy between humans and computers is a pretty good one. But either way, I am highly suspicious of the attempt to contrive an entire cosmology to fit one's preferred self-image for humanity. Whatever image that might be. Therein lies myth. That said, Smolin does have a number of independent arguments for the validity of his position that are well worth considering. I'll deal with those first before turning to the wider implications for human life. Now we're going to the zest of it. So I hope it doesn't start to rain here. Sorry, just gonna check it's still running smoothly and getting into the gory details, the interesting ones. The cosmological fallacy or the cosmological hypothesis. as we've established, the Newtonian paradigm that founds the computational vision of nature consists in two components. Initial state plus physical law. In arguing that time is real, Smolin would collapse the distinction between the two. His radical thesis asserts that all that exists is the present moment. Which is one of a succession of moments, and that the state of the universe in any one moment is therefore generative of physical law rather than slavish to it. Smolin's main battering ram against the prevailing belief in external laws is what he diagnoses as the cosmological fallacy in physics. All laws of physics, Smolin would remind us, are inferred from experiments conducted in small subsystems of the universe, laboratories mainly, and ought not to be automatically extended to the universe as a whole. And if a law describes that, which remains constant over many repetitions, of an experiment, then the idea of a universal law could never be scientifically warranted. After all, the universe only happens once. Smolin's arguments concerning the cosmological fallacy are extensive and interesting. But to my mind, almost entirely preempted by David Hume. In an inquiry concerning human understanding, 1748, Hume famously argued that though the patterns in the behavior of physical objects appear remarkably consistent, our faith in the uniformity of nature will always be impossible to prove outright. This is because whenever we try to justify our belief that the future will continue to resemble the past, we inevitably fall back on the excuse, well, it's always done so in the past! Exclamation mark. Which is a perfect example of circular reasoning. This is Hume in his own words. When I see, for instance, a billiard ball moving in a straight line toward another, may I not conceive that 100 different events might as well follow from that course? May not the first ball return in a straight line, or leap off from the second in any line or direction? All these suppositions are consistent and conceivable. Hume's arguments that the regularity of nature may be ultimately unprovable, and that radical changes are both consistent and conceivable, have long worried those philosophers keen to justify science's claim to eternal truth. The cogitations, however, have not been without fruit. Indeed, it's my view that Karl Popper's 20th century reply to Hume take much of the apparent force out of the issue. and by extension out of Smolin's cosmological fallacy. Popper, which is Sir Karl Popper, Popper's strategy was to concede that no amount of positive evidence could ever prove any theory to be ultimately true. But this is beside the point. Science for Popper should never be about demonstrating the truth of theories so much as throwing 1,000 guesses at a problem and seeing which one fall foul of experiment. Those hypotheses which could in some way be proven false but hold up are to be accepted as good science until counter evidence comes along. Smolin is in fact an avowed Popperian, but it strikes me that he is being inconsistent on this point. According to Popper's falsificationist model of science, the idea that the laws of nature may be timeless should not be considered a truth that requires justification so much as a working hypothesis that demands falsification. And I think we need to put a pause here. Getting a bit too rainy. Just when it's getting interesting. So we continue. We now change position out of the rain. Sorry about the little break here. According to Popper's falsificationist model of science, the idea that the laws of nature may be timeless should not be considered a truth that requires justification so much as a working hypothesis that demands falsification. And as Smolin himself admits, we have yet to see any hard evidence that the laws have changed since the Big Bang. Cosmological natural selection and the principle of precedence. But what about the Big Bang? Rather more persuasive than his attacks on the a priori validity of timeless generalization is Smolin's drawing attention to the two inputs the Newtonian paradigm takes for granted and could never itself explain. The initial state of the universe and the existence of laws in the first place. Smolin's solution to this perennial mystery in his theory of cosmological natural selection, and it is both wonderfully outlandish and deeply elegant. The argument runs that black holes may give birth to new regions of space-time whose laws undergo a subtle mutation in the process. The initial singularity in our Big Bang is thereby explained in terms of a quantum bounce from a previous era. The argument concerning laws, meanwhile, is essentially Darwinian. Those universes with laws conducive to the generation of black holes will have many progeny, while those with dramatically different laws will not. If our universe is typical, as the great majority will be, it will belong to the former camp. The theory, expressed mathematically, has even made some potentially falsifiable predictions about the nature of our universe, which enables Smolin to boast that he has satisfied the demands of good Popperian science. According to cosmological natural selection, physical law is only ever augmented at the birth of universes, but it requires that law emerge from some fact about the present state. Of the universe, in order for law to be malleable at all. if laws existed outside of time, they could never be subject to mutation. And hence natural selection and their origins would remain mysterious. But do the pressure cooker singularities at the hearts of black holes provide the only circumstances under which laws could change? Could they ever change during the lifespan of a universe? Or even during our lifetimes? Smolin's more recent proposal for the means by which laws may change, the principle of precedence, appears to raise that tantalizing prospect. Smolin lays the groundwork for this idea with an uncontroversial fact about quantum physics. If we prepare and measure, this is a quote, a quantum system we have studied many times in the past, the response will be as if the outcome were randomly chosen from the ensemble of past instances of that preparation and measurement. This apparent randomness is normally held to be consistent with timeless law because of the fact that the statistical distribution of the data remains constant over time. Study the position of an electron orbiting a hydrogen atom today. And you'll get the same spread of readings you got 50 years ago. But for Smolin, for whom the only reality is the present moment, all that exists is the ensemble of possibilities itself. And there is no timeless law governing their regularity. In the place of such a law, it is Smolin's contention that all we really need to assume is that nature repeats itself. This is the principle of precedence. To elaborate, it may be the case that any physical system when confronted with a question, we look to the past at all the other times a similar question has been asked, and pick randomly from previous results. The promise of this idea is that it makes sense of the success of Newtonian science, whilst leaving open the possibility that truly novel experiments or situations for which the universe has no precedent will yield truly novel results. Thus, for Smolin, the future is open, will yield, and we may be liberated from the idea that we can't do anything about it. Problems with the principle of precedence. It is at this point that I'm going to take a leaf out of Daniel Dennett's book. Pause, take a deep breath, and take the principle of precedence apart. I am readily attracted to Smolin's proposal that the regularity of nature may emerge from some fact about the present state of the universe, and may as a consequence be malleable in the singularities of black holes. The pressing need to account for the initial state of our universe and for the existence of its regularities strike me as perfectly valid motivations for taking these ideas seriously. I want to argue that the principle of precedence by contrast lacks any of the explanatory power of cosmological natural selection may well rely upon a deeply unscientific notion of consciousness in order to work. And actually serves to diminish the prospects of human freedom in the universe. I'll start once again. Se hur långt jag vågar spela in till. I'll start once again with the issue of scientific methodology. It is Smolin's bold claim that unlike the idea of timeless laws, the principle of precedence is truly scientific because it does away with all needless metaphysics and is itself checkable by experiment. But is it? Smolin cites, by way of a possible demonstration, the already extant practice of setting up quantum mechanical systems so complicated that they never yet existed in the history of the universe. If this principle is correct, then such a systems ought to thwart all theoretical expectations. And produce some genuinely novel phenomena. My problem with this is that expectations in science are thwarted all the time, especially in new areas of research. And when this happens, scientists can be relied upon to busy themselves with the search for alternative models and explanations. I find it hard to avoid the reductio ad absurdum that every thwarted expectation in the history of science ought to count as proof of Smolin's idea. How to tell the difference between a hitherto undiscovered but timeless fact about the universe that falsifies our expectations in this new area, and a spontaneously generated fact about the universe that confirms the principle of precedence. A true retreat from metaphysics ought to avoid begging such unanswerable questions, which is, I submit, the virtue of falsificationist approach I outlined earlier. A consistent falsificationist is agnostic about the ultimate truth of any theory. All they can know is that it holds up in the face of potentially falsifying evidence. It would make science an entirely trivial exercise to celebrate such theories when they work and at the same time claim to have validated some deeper principle every time they fail. Another problem with the principle of precedence is a lack of a convincing account of where genuinely novel phenomena are supposed to come from. If we are to imagine that for the most part of the universe glides along well-worn grooves, and only occasionally hit some bump in the road, that necessitates a spin of the quantum wheel and the settling upon some new mode of behavior. Then, what exactly constitutes that bump? To put it another way, if the present moment is both the source of all regularity in the universe and the blank slate upon which formative experiences are recorded, then from whence do such influences emerge? One possible answer might be from conscious human intervention. But if Smolin's thesis promises to justify the existence of a miraculous form of free will, then it ought not to presuppose it. Resisting that reading for the moment, perhaps it is the case that a generally deterministic universe will occasionally produce some set of circumstances so extraordinary as to bend itself out of shape. We've discussed black holes, but perhaps Smolin would have it that human intervention in the universe is likewise entirely determined right up to the point when, wholly governed by laws of physics, biology, psychology, we are moved to create some unprecedented situation or experiment which only then forges a new universal habit. But supposing we grant that possibility, what are we supposed counts as an unprecedented situation? How is the universe supposed to distinguish between unprecedented situations and familiar ones? Can it really tell that quantum physicists in 2013 are asking the same question when they repeat an experiment performed 50 years ago, when, for instance, our universe was smaller, our solar system was in another part of it, and the previous experimenter had a cold. I think I end there. I think this is an extension of the cosmological fallacy. And it's an interesting fallacy because it's not at all a fallacy in the normal sense. And of course, in some view, this was pre-thought about of the Scottish philosopher David Hume, when he questioned the idea, even if a billiard ball had come into this very same hole 1,000,000 times, we are not allowed to make that into a law. Doesn't matter how many times that regularity turns up. And I see often a similar argument against quantum indeterminism. It so seldom happens that we can, so to speak, push it aside, because most usually the world is classical. But therein lies the problem, because we have already proposed or hypothesized laws. And when we did that, we supposed them to be without any exceptions whatsoever. And now we are negotiating with them and saying we should keep the laws, but there could be some extremely unusual exceptions. And I would say that is not just. The foundation of the laws are still today that they are eternally, never failing, never ever failing, which is very important. And I would say that is the most important trait of any law. And I think most people have that, at least experience or feeling for it. I will continue in the next. I say thank you very much and have a very pleasant afternoon. Bye-bye for now. All lush and green here.